In this video, we're going to be going over the calculations for electric potential energy and voltage for point charges, as well as how to calculate the voltage from multiple point charges. And then finally, we'll be talking a little bit about equipotential lines. And then after that, we're going to go through some example problems. First, finding the voltage from multiple charges and ranking them at multiple points in space. Then a second problem, looking at the voltage from multiple charges in a two-dimensional situation. And then last, we'll be, again, ranking some voltages using this concept of an equipotential line. All right, so let's get started just talking about the electric potential energy and voltage for point charges. And mainly these are just equations, right? So the equation for the electric potential for a couple of point charges is going to be K Q1 Q2 over R, right? Looking very similar to our Coulomb's law with two or three notable differences. One, this is just an R, not an R squared in the denominator. Two, we're not taking the absolute value anymore, so this can be positive or negative. And then last, electric potential energy is a scalar and not a vector. So a situation, I could be having a positive Q1 and a negative Q2, and those two charges would be a distance r apart from one another, right? And I could calculate the electric potential energy of Q1 or Q2, and in both cases I'd get a number that should be negative. Now on the other side, I can be looking at the voltage for a point charge, and so the voltage for a point charge is just going to be K Q1 over R, where I'm saying that Q1 is the source charge. It's the charge that's creating the voltage, and then Q2 is the charge that's in that voltage and reacting to it. All right, so again, I could have a positive Q1, which is creating a voltage around it, and I could be looking at that voltage at a particular point, let's say P, and that point P, or wherever I'm looking for it, is an R distance away from my source charge. Now, you may be wondering where these equations come from. Let's start with the voltage. So with the voltage, we've said before that the voltage is equal to the electric potential energy divided by Q2, divided by whatever charge we're introducing into that voltage. And so if I put in my electric potential energy equation that I wrote down before, we can see that these Q2s are just going to cancel out, leaving me with my equation for the voltage. For the electric potential energy, the proper way to get to the electric potential energy is going to be using calculus, specifically that the potential energy generally is the negative integral of the force over some sort of distance or path r, dr. And so in this particular case, I can put in the electric force, so for point charges, Coulomb's law, and then that will output the electric potential energy. So for those of you in calculus, this is something that you could do to see that worked out. For those of you not currently in calculus, we're just going to have to kind of accept that there is a process out there for how we get this equation for the electric potential energy, but leave it at that. All right, so both of these are scalars, and we'll write down one more time, just reminding ourselves that the units for the electric potential energy are joules, and the units for the voltage is volts. And in order to get those units coming out on the other side, I have to use the charges in coulombs and the distances in meters. All right, now I may be interested in finding the voltage from multiple point charges. So for example, instead of just having one point charge that I'm trying to find the voltage like we saw above, I can have a series of point charges that are hanging out in space, and I can be looking for the voltage from all of these charges collectively at some point P. Now, simply to get the voltage from multiple point charges, I just have to add them up. All right, so the total voltage is just going to be the sum of the individual voltages on my system, in my system, at this particular point P. All right, so for my example, I might have Q1, Q2, Q3, each with their own distance away from the point, R1, R2, and R3. And so my total voltage at point P is going to be the sum. But again, remember that both the electric potential energy and the voltage can be positive or negative. And so in particular, because Q1 is a negative charge, that means it's going to have a negative voltage that it's creating. And so when I'm writing it in, I'm going to say negative K Q1 over R1. All right, now technically this is the absolute value of Q1. I don't want that double negative showing up, right? But or I could just say Q1 has a negative value and I could just write K Q1 over R1. Either way, we just want that voltage to be negative, right? And then I'm going to add that to K Q2 over R2 and K Q3 over R3. Right, and because voltage is a scalar, we don't have to be thinking about the direction, right? We just have to add up these individual scalar values to get our final answer. Right, and then last we can be talking about the equipotential lines. And equipotential lines are lines that we're drawing to represent the voltage surrounding a charge or series of charges. And mainly, or specifically, they are drawing out places where the voltage is equal, or the potential is equal, given the name equipotential. All right, so the lines representing equal potential. And so when we're trying to represent the voltage around a point charge, it's not quite as straightforward as with the electric field, right? The electric field is a vector, so we drew lines that were pointing in the direction that the vectors were pointing. In this case, we're trying to represent something which is a scalar, which is maybe a little bit different to us conceptually, but it is very similar to a topographical map. So in the notes that I put online, referenced topographical maps, right, as a way of diagramming and showing on a 2D space, right, something three-dimensional like altitude, where altitude is also a scalar. And so to a large extent, we can be thinking about voltage as sort of an analog to an altitude in a topographical map. Now, if I'm looking at a single point charge in space, right, I want to know where I'm going to have equal potential. So if I use my potential equation, KQ over R, right, Q is going to be held fixed, right, that's a constant value, K is the constant, so constant value. So we're going to have a constant voltage as long as the R value, my distance away, is held constant specifically. Right, and so if I'm trying to describe all the points that are a fixed distance away from my charge, I'm describing a circle. So the equipotential lines for a point charge like this is going to be a series of circles. Those are definitely circles that I'm drawing because I say so. And what these equipotential lines should be doing is marking off equal intervals of change in voltage. So for example, I could have this equipotential line that's closest be something like a positive 400 volts. And then maybe my next line is 100 volts away, so this would be a positive 300 volts. I'm getting smaller because we're getting farther away. And then this last one is a positive 200 volts, right? Constantly decreasing at the same rate. Now, in this case, I drew lines that I'm saying are 100 volts apart. I could do 10 volts, I could do 50 volts, I could do 1,000 volts. Whatever I want to do, right, I should have a consistent difference between the lines. So one of the things that we should be seeing is that theoretically, right, the distance between the 300 and the 400 volt lines is smaller than the distance between the 300 and the 200 equipotential lines. And so this is telling me that the voltage is changing more rapidly. And one of the ways that I can see this is actually looking at the diagram or the graph for the voltage. All right, so I've got a 1 over r relationship. So if I'm plotting a graph for voltage with respect to distance, I should end up with a graph that looks something like this. And now what we're doing is we're marking off equal segments. All right, so maybe I'm going like this. All right, so these are the equal intervals. So maybe this is my 100, 200, 300, 400, and 500. And then to see where those equipotential lines would show up, right, I can find the corresponding distance. Right, and again, we can see that the distance that's corresponding to these equally measured out intervals of voltage, right, are gradually getting farther and farther apart as we work our way down, right, just like the equipotential lines should be. Right, so part of what that's telling me is that different points on these equipotential lines, right, are going to have the same potential. So, right, both points A and B are going to have 300 volts. Something like C, right, is going to be at 200 volts. Something in here like D would be 400 volts. Any other point on the same line, E, right, is going to be 400 volts. And so it's a way of representing and showing physically what these where these voltages are going to be. Another way that I can think about this, and we like drawing this on 2 dimensions, but I can also just do my best to give you a 3-dimensional picture of what this is going to look like. So I'm essentially taking this voltage as a function of distance r graph and rotating it around the y-axis to get a rough picture of what this is going to look like. So for a positive charge, I would have a 3-dimensional shape that looks something like this, right, where it's probably just going to keep going up until it reaches some sort of point, but we'll just kind of cap it at some value. And so this is a 3-dimensional funnel looking thing, right, and this is how we're mapping out. It's kind of the topography of our voltage surrounding our charge. And I can do a similar thing for a negative charge, except if the charge is negative, that means all my voltages are going to be negative as well. So rather than increasing positively to some sort of peak, it's going to be decreasing negatively to some sort of bottom. Right, and so sort of like a diagram that you might have seen of like a black hole. Right, I can create a sort of 3-dimensional diagram of what the voltage is going to look like, right? Everything decreasing downward into this pit for the voltage. All right, so that's the gist of what we want to be looking at, right? The equipotential lines, the voltage from multiple point charges, and then broadly calculating the electric potential energy and voltage for point charges. So let's switch over to the example problems and start working through them. All right, so each part of the diagram shows 3 points in the vicinity of 2-point charges. The charges have equal magnitude, and we're trying to rank in order from the most positive to the most negative the potentials of V1, V2, and V3. All right, so I'm going to work through the first one in a lot of detail just to make sure that we've got the idea. First of all, we're going to give each of these a value of Q, and we'll do this for all of them. They're all the same charge, so we'll just have a positive Q and a negative Q. The other thing that we can say is that these points are equally spaced between the charges and from the charges. All right, so I can say that this distance is going to be just some value r, but that means that this is also r, this is r, and this is r. And that will be the same for part B as well. So what I can do to calculate the voltage at point 1, right, is add together the voltages from the left and the right charges. All right, and so voltage at 1 is going to be kq over r from the left charge, right? It's an r distance away to point 1. And then for the right charge, I've got a distance of 1 to 3r, and so I'm going to do kq over 3r. And if I factor this out, I would get kq over r times 1 plus 1/3, right, or 4/3 kq over r. All right, we can do this again for point 2. So the voltage at 2 is going to be from the left charge, kq over r, and from the right charge, kq over r. Right, both charges are an r distance away, so I'm just going to add them together and get 2 kq over r. And then lastly for V3, I'm going to let you take a second and think what the answer for this should be based on where the point is and where the two charges are. Right, and we should end up finding that the voltage at point 3 is going to be the same at point 1. So the left charge is going to be kq over 3r, right, again 1, 2, 3r from q left charge to point 3, and then kq over r for the right charge. And so this is the same as what we had up in V1, or the voltage for point 1, and so we're going to get 4/3 kq over r. All right, so in terms of ranking these from most positive to most negative, all right, they're all positive. We've got nothing but positive charges in the area, and so I can say that V1 is the, nope, excuse me. I can say that V2 is the most positive, right, and V1 and V3 will be equal to one another. Okay, so for part B, we'll go just a little bit faster. So I'll start with point 1, and again, both of these are Q, all of the R distances away. So for voltage 1, right, so hopefully we're getting that distance R and 3R. We're feeling comfortable with that for point 1. The only difference in this case is that the right charge is negative, and so it's contributing a negative voltage. So instead of the 4/3 that I got last time, I'm going to have 2/3 this time. Right, then for V2, I should take a second and try and predict what this will be. But V2, right, we've got the same R distance between the positive and the negative charge, so it's a positive kq over r from the left charge and a negative kq over r for the right charge, right, giving me a final answer of 0. And then finally for V3, at point 3, the voltage at 3, I'm going to have something similar to what I did in part 1, but the positives and negatives are going to be flipped. So I'll have a negative kq over r for the right charge and a positive kq over 3r for the left charge. So my final ranking, V1 is the most positive, and then V2 with 0, and then V3 for the negative voltage. But we can also note that the magnitude of, or that, excuse me, the absolute value of the voltage at point 1 is equal to the absolute value of the voltage at point 3. All right. For parts C and D, we're looking at points that are on that perpendicular bisector between, on the line between these two charges. So one above, one right in the center, and then one the same location below. Now for this, I'm going to want to introduce a couple different variables. All right, so I'm going to say this distance from either of the charges to the center point is R2, and then from here up to, from the left charge up to point 1, I'll call that R1, but it is going to be the same down at the bottom. It's the same distance from the charge down to 0.3 as well, and then same thing on the other side. And that definitely looks like a 4. Alright, so for point 1, I'm going to have a voltage which is KQ over R1 plus KQ over R1. And then for the voltage at point 2, and for point 3. So already we've established that the voltage for 1 is equal to the voltage for 3 at point 1 and point 3. And we just need to rank the voltage at point 2 relative to those. So one of the things that we'll want to note is that R2 is less than R1. So when I'm looking at this equation generally, that the voltage is equal to KQ over R, that's going to tell me that as the distance between the point and the charge increases, then the voltage is going to decrease. So larger the distance, smaller the voltage. So R1 being larger tells me that the voltage is going to be smaller. So the voltage at 1 and 3 will be less than the voltage at 2. Right, and then last we can do part D with the same sort of variables being used. And in this case, we're seeing that all 3 of the voltages are going to end up being 0. And this should make a little bit of sense. One charge is positive, one charge is negative. So we already know they're going to be canceling out a little bit. And then for points 1, 2, and 3, it's the same distance away for each of those points for each of the charges. So we're getting a 0 volt. The other thing that's telling us is that if I have a positive and a negative charge, at the center of the line that's connecting between the two of them, we have an equipotential line. Not quite in the center. Let's try that again. You have an equipotential line of 0 volts, right? There's a line that's representing this equal potential of 0 volts as long as we are on the line that's going right in the middle of those two charges. Okay, so I guess we can finish this one up. V1 is equal to V2 is equal to V3. Alright, so the main points that we're trying to see at this point, to find the voltage from multiple point charges at a point in space, we're just adding together the voltages from each of those point charges using that equation, KQ over R. And for positive charges, it's a positive voltage. For negative charges, it's a negative voltage. Alright, so let's use that to move into problem number 2. So in problem number 2, I've got this square with charges at the edge, or at the end, excuse me, at the vertices, and I'm looking for the electric potential at the point indicated in the figure. Alright, so specifically this point right in the center. So I'm going to work this out longhand first, right? So first thing I need, if I'm looking at the equation, that the voltage is equal to KQ over R, I've got Q, right? So 2Q, 2Q, negative 2Q, and Q. So I've got the charges for all of these. K is just that constant, 8.99 times 10 to the 9th. But R, the distance from a charge to the point, or to a point, I don't know. So what I need is this distance R. And it will be the same for each of these. If it isn't obvious from my rendition of the diagram, all right, the point is in the middle of this square with the 2 centimeter sides. Now to find this distance R, I can use a right triangle in any one of these. I guess let's go down here. So I'm going to form a right triangle where the sides of my triangle are 1 centimeter and 1 centimeter. And now my R is the hypotenuse. And so R is going to be equal to the square root of 0.01 squared plus 0.01 squared. And that gave me a value of 0.014141 meters. All right, so then to find the total voltage at that point, I'm just going to add them all up. So I'm going to start at the upper left-hand corner and work my way around clockwise. So I'm going to have a positive K2Q over R plus K2Q over R plus KQ over R minus K2Q over R. Now to simplify this, I can actually factor a lot of this out. So the coefficients 2, 2, negative 2, and 1, which is going to give me a final coefficient of 3. So the final voltage will be a 3kQ over R, which is giving me a value of 3.24201 times 10 to the 6th volts, or in two significant figures, 3.2 times 10 to the 6th. All right, now that's the long way to get through this, but there is one way that's a little bit faster if I just stop and look at the problem before I get started. So once we've established that these are all the same distance apart, then we know that the voltage is only going to increase or decrease based on how much charge they have. And so when I'm looking at this, I can look at the upper right-hand corner with the 2Q and the lower left-hand corner with the negative 2Q, and I can say right off the bat, those two voltages are going to cancel out. Right, so I've got positive from one, negative from the other, same magnitude charge. Those are going to have a net zero effect. And so then I'm just left with the upper left-hand charge and the lower right-hand charge of 2Q and Q. So those two are going to be added together, and so it's the same thing as a K3Q over R. Right, same thing that we ended up getting before. If you don't feel like doing it that way, that's okay. But just know that there is a way that we can get through these problems a little bit faster if we stop and look at them sometimes. Okay, and last, looking at the equipotential lines, we're going to rank in order from most positive to most negative the electric potentials V1 to V5 at the points 1 to 5 in the figure. So there's a few things I'd like to point out first. One, we've got a negative charge in the center here. So that means that all of the voltages that are being created are going to be negative. Right? After that, I can look at these equipotential lines that I've got, and I can notice that 2, 3, and 4, the points 2, 3, and 4 are all on the same equipotential line. So before I even do anything else, I can just say that the voltage for 2 is equal to the voltage from 3 is equal to the voltage from 4. Right? That's what these equipotential lines are telling me. That they have equal potential at all points on that line. Same thing is going to be true for 1 and 5. That V1, the voltage at point 1, is equal to the voltage at point 5. So in terms of actually ranking them from most positive to most negative, the main thing we need to do is rank these charges, sets of charges, excuse me. So one of the things that I can cue in on is these points 4 and 5. Right, because it makes it easier to see that they're in line with one another. It's just that one is farther away than the other. So I can say that, let's say R5 is greater than R4. Right, the distance to 0.5 is greater than the distance to 0.4. Now what we said before was that as the distance increases, the voltage decreases. But let's be a little bit more specific. It's the magnitude, it's the absolute value of the voltage that's going to be decreasing, right? The voltage is going to get smaller in its numerical value, right? But it's not going to decrease as in it gets more negative, right? So what I could do, for example, to help with this is to add some numbers to these equipotential lines. Again, it doesn't particularly matter what numbers I use, but I could say this is negative 1500 volts, and then this is a negative 1000 volts, 1000 volts, and then next is a negative 500 volts. All right, so I'm starting at a negative value, and as I move outward, it's getting less negative. Right? The magnitude is getting smaller, but it's also just getting less negative. So if I'm going from the most positive to the most negative, then the voltage at points 5 and 1 are going to be the most positive or the least negative. So if I was ordering these, I would say V1 is equal to V5, right? That's the least negative for the most positive, and then next is going to be the V2, V3, and V4, voltage at points 2, 3, and 4. All right, so that about wraps it up. Looking at the calculation for point charges from the electric potential, energy, and voltage in the equipotential lines. So as you're working through your own practice problems, you're running into any trouble, let me know, ask your questions, and otherwise, good luck out there.